Okay. Now we can consider an example, okay, of this typology of differential equation. Y dot t equal to minus 3 y of t. We want to solve this differential equation. Sorry. Applying the same methodology we have seen before. So we have y dot t plus 3yt equal to 0. This is the first step, and it's not difficult. Okay. Now we need to multiply both sides by the integrating factor, and the integrating factor is e to the power of 3t. Before was e to the power of 8t, now e to the power of 3t, because now a is equal to 3. The constant is equal to 3. Okay, this first side of the equation is the derivative of yt, which multiplies e to the power of 3t respect to time. And we can check this condition together. It's not necessary, but now we can check this condition, because if we compute this derivative respect to time, this is the derivative of a product. Tell me the problem now. So the derivative of the first is y dot t, by definition, the derivative respect to time. The second is e to the power of 3t. Now, this is not enough. We need to add the first y of t, which multiply the derivative of the second function. What is the derivative of the second function respect to time? Is e to the power of 3t, which multiplies 3. We need to multiply by the derivative of the exponent. Sorry, the derivative of e of t is e of t. The derivative of e to the power of 3t is e to the power of 3t, which multiply 3. Because we need to multiply by the derivative of the exponent. And this is equal to this if you collect e to the power of 3t. You can try, but are the same. I can collect for you y dot t plus 3yt, which multiplies e to the power of 3t. The same. So the reason why we multiply by e to the power of 3t is to obtain this derivative in order to solve the differential equation. Okay. Now, our differential equation is the derivative of y of t e to the power of 3t respect to time equal to 0. And now it's easy to solve this because we can integrate both sides respect to time, integral and integral in dt and dt simplify, integral a differential inverse function. So the first side becomes yt e to the power of 3t. Okay. So on the second part we get c. So our final solution, general solution, can be obtained because we need to isolate y of t. So we need to multiply by e to the power of minus 3t both sides, because this is 1. Can you see that this is 1? So our general solution is yt equal to c e to the power of minus 3t. This is the general solution. Why it's a general solution? Because there is the constant c. So we have a set of functions, not just one function. If c is equal to 1, you have one function. If c is equal to 2, another function. So you have a set of functions. Now, suppose that the initial value, okay, this it's interesting. The initial value is 0. So at time 0, the value, it's not correct. The initial value is 1, is 1. Okay? If the initial value is 1, from the general solution, we can see that the constant is equal to 1. Substituting t equal to 0 times 0, and y of t equal to 1.
So,
yes.
The last one you write it's a particular solution?
No, the particular in order to derive the particular solution, we need to compute the value of the constant. And the value of the constant can be obtained from the general solution by some initial condition. If the initial condition is y at time 0 equal to 1, the constant is equal to 1, and the particular solution is 1 which multiplies e to the power of minus 3t, because the constant is 1. So this is the particular solution of this differential equation. Can I delete? Yes. So, if we consider the particular solution, I write again y of t equal to e to the power of minus 3t, because it's 1, so we can also write in this way. What is the dynamic of this system? Well, I mean, if time goes to infinite, this function decreases and reach 0. Okay? Does not reach 0. Converge tends to 0. Okay? What I'm saying is that the limit as time goes to plus infinite, because we go at the end of the universe plus infinite, okay, of e to the power of minus 3t, this limit is equal to 0. Why this limit is equal to 0? Because the exponent is negative. So you get e to the power of minus 2 equal to the power of 2 billions, e minus 2 billions. It's a smaller and smaller number. So we convert to 0. So in this case, we know that the equilibrium solution of this dynamic system is 0. And we know also that this solution is stable, is globally stable. Because also if we start from 1, we will converge to 0. If we start from 1 billion, we will converge to 0. So 0 is a stable solution. Is a stable equilibrium solution. If we are here, okay, this is a stable equilibrium solution. Because also if we start here, this is the final equilibrium solution. Also, if we start from here, this is the equilibrium solution. So this is the stable equilibrium solution. It's the same in physics, okay? If we are here, this is an equilibrium solution, yes, but it's not stable. Because if we start from here, we go here. If we start from here, we go here. So it's not stable. It's an equilibrium solution, but it's not stable. In economics, it's the same. The solution 0 in our differential equation is an equilibrium solution, and it's also stable, globally stable. Globally because for each initial condition we will converge to 0. Also if we start from 10 billions, we will reach 0. I show you again the initial differential equation. Our initial differential equation was y dot t equal to minus 3yt. This is our initial differential equation. Now if we consider this differential equation, it's easy to understand that y equal to 0 is the equilibrium solution. Because y dot of t will be equal to 0 if and only if y of t is equal to 0 from this equation. If y is equal to 0, also y dot is equal to 0. It's a simple first order equation. But so y equal to 0 is an equilibrium solution because we can interpret the derivative with respect to time as the speed of this variable. If the speed is equal to 0, we are in equilibrium. Y dot equal to 0 implies that the speed of this variable is 0. The speed of this exchange rate is 0. The speed of this object in the space is 0. So it's an equilibrium. And what is the value of y which gives a speed equal to 0? Is y equal to 0 in this case. So y, the solution that we can call y star, which is the equilibrium solution, is 0. Is the equilibrium solution. And we are sure about this. Is the equilibrium solution. But another way to check if this solution is stable or unstable, we know that this is stable. Okay, but another way to assess the stability is to consider a picture in which we have y dot respect to y. The relation between the speed and the value of the variable. This is also called phase diagram. Diagramma di fase. Phase diagram. What is the phase diagram in this particular case? We can draw the linear relation between y dot and y. It's a linear relation. This is the relation. It's a straight line, okay? I draw again. Sorry. Is another way to assess the stability. Oh, mamma mia. Sorry. Again? No? Proprio è l'orario, ok. No, non funziona. Un loop. Sorry. Ok. Sorry. It's the best it's the best possible line. Okay, this is the relation. Here you have y dot, and here you have y. Okay. The point is, the equilibrium solution y star is this one. It's 0. It's the origin. Okay. Why this? We can see from this picture that y star is stable. Because suppose we are here, as in the previous case, the initial value is 1. This implies that derivative with respect to time is negative. Negative speed. So the variable reduces. If the negative speed is equivalent to say that the value of the variable reduces. Is a negative change respect to time. So a reduction in this variable. If we start here from this value, for instance, -2, -3, -2 billion, what you want, in this case the speed is positive. Y dot is positive. The derivative with respect to time is positive. This implies that the variable increases. The value increases. So we converge toward our stable equilibrium solution. This is a case of stable equilibrium solution. You can also start from 1 billion, 2 billion. You will converge to 0. Okay? A mechanical way to see this is if the coefficient of y in the differential equation is negative, the equilibrium will be stable. If it's positive, the equilibrium will be unstable. I will show you the example. If the differential equation is is y dot equal to 3y and to function of time, what is the phase diagram in this case? The equilibrium solution is the same, because y dot will be equal to 0 if and only if y is equal to 0. So the equilibrium solution, which gives speed equal to 0, is y equal to 0. So if the variable assume the value 0, the speed will be equal to 0, and so we are in equilibrium. The problem is to check if this equilibrium is stable or unstable. is unstable. I will show you now. Because the phase diagram, what is the phase diagram? Is y dot respect to y. If we consider the differential equation is a straight line, but it's an increasing straight line because the coefficient is positive. Capolavoro. Okay. In this case, y star is an equilibrium solution. But you can see that this is unstable. Why? Consider an initial value equal to this, for instance, 1, 2, 3, what you want. The speed is positive or it's negative? It's positive. But if the speed is positive, the variable grows, increases. So we diverge from the equilibrium. If we start from here, it's the same, because here the speed is negative. But if the speed is negative, the variable decreases, the value decreases. So we go in this direction. So yes.
We have two solutions for the limits in this case.
Yes, because you have plus and minus infinite. It will depend on the initial condition. Sure. In the previous case, you have one solution. So in this case, you diverge from the equilibrium, which is an equilibrium, but it's globally unstable. Because if you start from a point close to y star, you will diverge to infinite, plus infinite, or minus infinite. So it's globally unstable.
We have a stable equilibrium, but we have only a solution.
You have an equilibrium solution which is unstable.
Yes, in this case, but when we can find a stable equilibrium? Only when the limits plus infinity or minus.
When the limit.
It's only one solution.
One solution. No, maybe you have also, if you mean several equilibrium points, you may have also more equilibrium points. In this case, it's linear, so you have just one equilibrium. If you have a quadratic differential equation, you may have two equilibrium solutions. You can check if they are stable or unstable. But maybe that if you have two equilibrium, they are not globally stable. Because if you start from one point, you can reach one equilibrium and not the other one. But consider just one equilibrium is enough for now, okay? So this is a very easy way to check for the stability of an equilibrium. We can generalize this differential equation yes, we can generalize I know it's too difficult for you, but I think it's useful because we can have a differential equation y dot of t equal to a y of t, which is the same we have seen before, plus b plus a new constant. This is just to introduce the possibility of equilibrium solution other than zero. But before we have to solve this differential equation. The equilibrium, it's easy to find the equilibrium solution The equilibrium solution is the solution which gives speed equal to 0. In order to have speed equal to 0, a y plus b must be equal to 0. So the right hand side, and this is true if y is equal to minus b over a, which becomes our equilibrium solution. Before was 0 because b was 0. Now, if b is other than 0, the equilibrium solution is minus b over a. Because given this value for y, the derivative with respect to time is 0. So we are in equilibrium. And also in this case, the stability of the equilibrium depends on the coefficient a. If a is positive, the equilibrium will be globally unstable. If a is negative, the equilibrium will be globally stable. It's the same we have seen before. The only difference is that now the equilibrium is not 0, but it's a positive or a negative number according to B and A. Yes?
If A is negative, equilibrium solution is
Okay, if A is negative, the equilibrium solution is globally stable. As in the previous case. If A is positive, the equilibrium solution will be globally unstable. Because if A is positive, the slope is positive. If A is negative, the slope is negative. It's the same we've seen before, but now the equilibrium is not 0, it's a positive or a negative number, depending on B and A in the exercise. Okay? For instance, if B and A are both positive, the equilibrium solution will be a positive number. No, will be a negative number if are both positive, and will be globally unstable because A is positive. But I will show you with an exercise. Now we have to solve the differential equation. If you want, we can say now if A is positive, y star is globally unstable. If A is negative, y star will be G, globally stable. You can understand this point, okay? How we can solve this differential equation? The procedure is the same we have seen before, with the integrating factor. So the differential equation becomes y dot t minus a y of t equal to b. B remains on the right hand side as 0 in the previous case. Now we need to multiply both sides by the integrating factor, which is the same we have seen before. The integrating factor is e to the power of minus at. Why we have this integrating factor? Because now you can write the left hand side as the derivative of yt, which multiply e to the power of minus ct. So the first side becomes the derivative of y of t e to the power of minus at respect to time. and the second side remains the same. Now we need to integrate both sides of this equation. The difference is that now the right hand side is not 0, but we can compute this integral, okay? So the first side integrate in dt, and the second side integrated in dt. The first side becomes dt, d, and the integral. Simplify, but simplify is not the correct word because the differential and the integral are inverse functions. But we need to compute the second part, the second integral, which is it's easy to compute. So in this case, we have yt e to the power of minus at equal to the integral of b e to the power of minus at in dt. So we need to compute this integral. The first side is the same. In order to compute the integral, b is a constant, so we can put upside the integral b here, okay? Because b does not depend on time, okay? And we need to compute the integral of e to the power of minus at. How we can compute this integral? The problem is that we have e to the power of minus at, but we cannot see the derivative of minus at, which is minus a. So we need to incorporate minus a in the integral without changing function. So a way is to multiply and divide by minus a. I show you now. b, which multiplies e to the power of minus at, which multiplies minus a and minus a, we multiply and divide by minus a is the same because it's equivalent to multiply by 1, okay, in dt. I can put outside the integral the denominator minus a, so we get minus b over a integral e to the power of minus at, which multiplies minus a in dt, because our aim was to obtain this function. Because we need to have minus a in the integral, otherwise we are not able to compute the integral. So we have minus b over a. What is the integral of the function inside the integral? Is e to the power of minus at. Because if you compute the derivative of e to the power of minus at, you get e to the power of minus at, which multiplies minus a. Because you have to multiply by the derivative of the exponent. Do you agree that the derivative of this is this? Plus a constant c. Okay, we need a constant because we are solving an integral. So we have y of t e to the power of minus at equal to minus b over a e to the power of minus at plus a constant c. We can obtain y of t from this equation. It's enough to multiply by e to the power of 80. 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 We are multiplying both sides, okay? So we get y of t equal to minus b over a, which multiplies 1, okay, plus c e to the power a t. Our general solution. This is the general solution. It's the same we have seen before, but now we have minus b over a. Before was equal to 0. It's the same general solution. So the previous case was a particular case of this general case. Okay? Was the case in which b is equal to 0. But we know also that minus b over a is the equilibrium value of y. So this solution can be also expressed as y of t equal to y star plus c e to the power of at, because minus b over a is the equilibrium of y. We have computed in the initially in the differential equation. Y star was minus b over a. Now, using some initial condition, we can get the particular solution. For instance, if the initial condition y of 0 is equal to y0, initial value of y is y0, from the general solution, what we get? The general solution becomes y0 equal to minus b over a, y star is the same, y star, plus c. From the general solution, you get this? Yes, because it's c which multiplies c to the power of 0, which is 1. This implies that c is equal to y0 minus y star. The constant is the difference between the initial value of the variable and the equilibrium value of the variable. So what is the particular solution? The particular solution will be y of t equal to y star plus y0 minus y star, which is the value of the constant in the particular solution, which multiplies e to the power of at. This is the particular solution. But this particular solution, it's not so strange. Why? Because in equilibrium, the value of y is y star. If we start from a point other than y star, greater or lower, but other than y star, the difference between the initial condition and the equilibrium will converge to zero if A is smaller than 1. Sorry, smaller than 0. I mean, here you can see the difference between the initial value and the equilibrium condition. If the exponent A is smaller than 0, as time goes to infinite, this difference will become lower and lower. It will converge to 0. So the y star becomes a stable equilibrium solution. From here, if A is lower than 0, y star globally stable. I'm considering the same conclusion we have seen initially. But if A is greater than 0, in this case, the difference between the initial value and the equilibrium will increase as time goes to infinite. So y star is an equilibrium solution, but is globally unstable. But we know this from the phase diagram. It's just another way to see the same concept. So if we consider an example, so if we have y dot of t equal to minus 3 y of t plus 2, okay? What is the equilibrium solution of this differential equation? Which is also called steady state in economics, okay? The steady state solution. Steady state. State solution. The steady state solution implies that the speed is equal to 0, so minus 3y plus 2 is equal to 0. So y, the steady state solution is y equal to 2/3. We can call it y star because it's the equilibrium solution. Now, is this solution stable or unstable? Stable or unstable? Stable or unstable? Stable, because the coefficient is negative. If we are not sure, we can draw the phase diagram. We can draw the phase diagram. Wonderful phase diagram. Y dot respect to y, the equilibrium is 2/3. The slope is negative. Okay? The slope is negative. This implies that if we are here, the speed is positive, and we converge towards 2/3. If we are here, the speed is negative, so we converge again towards 2/3. So 2/3 is globally stable. Is globally stable equilibrium. It's easy to check because the coefficient is negative, -3. If you have 3, the coefficient is positive and is globally unstable. But if you have 3, the equilibrium solution becomes -2/3. Okay? Which is globally unstable. In this case, the equilibrium solution is 2/3 and is globally stable. What is the solution, the general solution of this differential equation, general and particular solution? We have to do the same computation. The same computation is y dot plus 3, sorry, of t plus 3y of t equal to 2. We put on the left hand side. The integrating factor is e to the power of what? 3t. Oh, 3t. We need to the first side can be written as the derivative of yt, which multiplies e to the power of 3t respect to time, while the second remains the same. Now we need to integrate both sides respect to time. We can simplify. The first side becomes y of t e to the power of 3t equal to 2 times the integral of e to the power of 3t in dt. What is the integral of e to the power of 3t in dt? We need to multiply and divide by 3. So we can consider 3 here and 3 here. We divide and multiply the integral by 3. If you put inside or outside the integral is the same, okay? And what is the integral? The first part is the same, 2/3, and the integral is e to the power of 3t plus a constant c. Because the derivative of this is this. I'm sure you can see. What is the derivative respect to time of e to the power of 3t? E to the power of 3t, which multiplies 3. Are you able to derive y of t from this equation? We need to multiply both sides e to the power of -3t. So you get y of t equal to 2/3 plus c e to the power of -3t. This is the general solution. Okay, I know you are afraid about what I'm doing now. You can also apply this, what I've shown to you is all the mathematical step. Okay, but you can apply also the general solution we have seen to solve the exercise. Okay. Problem is, this is the general solution, okay? So the general solution is y of t equal to 2/3 plus c e to the power of minus 3t. This is the general solution. But 2/3 is what? Is the equilibrium solution. Y star was equal to 2/3. So the general solution is y of t equal to y star plus the constant e to the power of minus 3t. This is the general solution. In the particular solution, we need some initial condition. If, for instance, y of 0 at time 0 is equal to 3, what is the particular solution? We have 3 from the general solution equal to y star plus c, which implies c equal to 3 minus y star. But we know that the constant is the difference between the initial value and the equilibrium value. So the particular solution will be y of t equal to y star plus 3 minus y star, which multiplies c to the power of minus 3t. If you want to emphasize y star, if you want to compute the value, you can substitute 2/3 and write the exact solution. But this solution allows us to see again that we start from the equilibrium condition. If we start from the equilibrium condition, this system is in equilibrium. But if we start from 3, which is different from the equilibrium condition, we will converge to the equilibrium solution if time goes to infinite, because the coefficient is there. I'm repeating the same concept, but this is the crucial point in differential equation. So we start from the equilibrium. If we start from a point other than the equilibrium, we will converge to the equilibrium. So the equilibrium is stable, it's globally stable. If you want, we can also represent y of t, also if it's not necessary. Oh, you are right. Thank you. Time, y of t start from 3 at time 0, the equilibrium condition is 2/3, and the dynamic is this. We will converge toward the equilibrium condition as time goes to infinity. So our equilibrium condition is stable. If you start from 0, you have the same dynamics. What happens if you start from 0? If you start, what I'm saying, if you change the initial condition, y of 0 is equal to 0, okay? In this case, the particular solution becomes becomes 0 equal to y star plus c so the constant c is equal to minus y star, and the particular solution is y of t equal to y star minus y star, which multiplies e to the power of minus at. And the function will be something like this. Okay, this is not correct, but y star implies that this is negative. So the difference between 0 and y star decreases if time increases. And we will converge towards, also in this case, toward the equilibrium solution. So the dynamics, should be this, should converge towards the equilibrium solution, because the solution is globally stable, okay? This is just to show you y of t respect to time, but in order to check the stability, it's enough to consider the phase diagram. So we don't need to check using this picture.
So if you start from 0, it will be globally stable.
Yes, globally stable means that if we start from 0, from 1, from 2, from 2000, you will converge towards the equilibrium solution, 2/3 in this case. Okay? I know I'm killing you. maybe if you consider the general solution, general case, the general case is y dot t equal to a yt plus b. This is the general case. You can also make mechanic this process in some way, but you know that there is a computation underlying. If this is the general case, you know that the equilibrium solution is minus b over a. It's just a refresh, okay? This equilibrium solution, y star, will be globally stable if a is lower than 0. It will be globally unstable if a is greater than 0. The general solution is y of t equal to y star plus y0 minus y star, which multiplies e to the power of 8t, where y0 is the value of the variable at time 0, is the initial condition. This is the general solution. No, sorry. This particular solution. This is the particular solution. Okay? Under the assumption that the initial value is equal to y0. The general solution is y of t equal to y star plus c, which multiply e to the power of 8t. Is what we have seen today. And from here you can see that the equilibrium solution is stable if a is lower than 0 and stable if a is greater than 0. Now the problem is that we have solved the differential equation and we finish with the computation, okay? The problem is that we have seen differential equation solving differential equation backward. This differential equation have been solved looking at the past, looking at the time between 0 and today. During the past, you are able to describe the dynamics of this variable. The problem is that in economics, economic variable depends on future, are not, in physics, variables depends on the past. My position now depends on my previous position. I was here. If now I am here, my position depends on my previous position, okay? In economics, this is not the case. Because in economics, if the future change, also the current situation change. If the expectation about the future change, also the value of the variable today change. In economics, we have the expectation. Some variable can be considered as backward looking. So the capital stock today is given by the sum of all the investment in time. But other variable, like the exchange rate, for instance, depends not only from the past, but especially depends on the future. You know this. So the problem is that in economics, variable can jump. In physics, I cannot jump. It's not possible now I'm here and you visualize me in Abruzzo, okay? In next second. My position now depends on the previous position. In economics, an economic variable can jump from a position to another position. Why? Not because the past has changed, but because the expectation about the future changed. And I think this is the what make interesting economics respect to the other sides. Just to see an example. It's not mathematics, okay? If you consider an economic variable at time t0, it's possible that this variable jump. This is possible in economics. And actually, in the monetary model to determine the exchange rate jump because of changing expectations. Okay? I think it's enough for you. Or not? I will be here for questions, okay? For any question. Finisco la registrazione.